I want to design a burglar alarm system using a few bipolar transistors, some resistors, and perhaps a few capacitors. I'm going to draw this system as just a box. And when this burglar alarm is triggered, I want it to drive a siren that I'll show as this. This is my ground symbol. And I'll draw a resistor here for the siren. Now when this siren is triggered, it's going to emit sound waves. And for a trigger mechanism, I want to use a simple switch. And this terminal of the switch is connected to ground. And so when the intruder comes into my home, there's going to be some way he's going to trigger the switch. He's going to close this switch, connect these two terminals together, and I want this siren to sound for perhaps a minute or so. And I want this system to run on a 6-volt battery. In case my house power gets interrupted, the burglar system still works. And I want the current in standby drawn from the battery to be as close to zero as possible. So let's say I from the battery B is equal to 0, or as close to 0 as we can get until it's triggered. When it's triggered, it can draw a lot of current. And when it's triggered, I want the alarm to sound for perhaps 60 seconds, plus or minus. It's not real critical. So in this video and in the next several videos, I will be explaining how to design this circuit using bipolar components, resistors, and capacitors. And if you can follow and understand this design, you will be on your way to becoming a good bipolar circuit designer. Recall that in the video on the NPN transistor, we designed a simple amplifier circuit. We had a 2K resistor. We had a NPN bipolar transistor with an emitter resistor tied to ground. We said the base voltage was set at 1.7 volts. We said this was 2K, this resistor was 1K. And then in the video on the PNP transistor, we added a transistor to this circuit, a PNP transistor with the emitter at the supply voltage. And the collector went off to a 1K resistor that went to ground. Now I have two ground symbols, so you can think of these grounds as connected to each other. Now recall that this bipolar transistor, the PNP, was in saturation. So let's modify this circuit a little bit. I'm going to erase some of it. Let's erase this part. Let's erase this PNP collector resistor. Let's connect the circuit a little differently. Let's take this collector of this PNP, and I'm going to connect it to a resistor to the base of the NPN, to another resistor to ground. And let's say that this resistor is 10K and this resistor is also 10K. So let's figure out what the circuit does. Now, for example, let's say that this transistor is off. If that transistor is off, we have no base emitter current. We have no collector current. If we have no collector current, this resistor pose the base of the PNP up to the supply voltage. I'm going to call this 6 volts. Since before it was 5 volts, but we're going to use a 6 volt battery. So I'm going to change the supply level to 6 volts. So if this transistor is off, this transistor is also off. And so this base voltage on the PNP is sitting at 6 volts because this NPN is off and there's no current running through it. And since the PNP transistor is off, our 10K resistors pull everything to ground. So this is at 0 volts here. The base of the NPN is at 0 volts. And the circuit's happy. Everything's off. It's conducting essentially no current. There's this very slight reverse diode current in this junction and in this junction. So this base is at 6 volts and the collector is at ground. So this diode, junction diode, is reverse biased by 6 volts. The collector of the NPN is also at 6 volts and the base is at ground. So this collector base diode is reverse biased by 6 volts. So there's a very infinitesimal leakage current through this reverse bias diode and through this reverse bias diode. So this circuit meets my standby condition for the alarm system of essentially 0 current. Let's analyze what happens. Let me erase this off condition. Let's presume that one of these transistors is on. Let's say that the PNP transistor is in the on condition. And that means that we're running some current out of this base, and there's current in the collector circuit that flows through these two 10K resistors. So it flows through here. And that increases the voltage at the base of the NPN. And when that happens, this transistor turns on also. And when the NPN transistor is on, we get an emitter current. Essentially, all that current flows through the collector, and it feeds the base current of the PNP, and the PNP transistor stays on. So once one transistor goes on, they both go on. This circuit is called a latch. It can exist in two states. It can exist when both transistors are off and when both transistors are on. And when both transistors are on, the voltage at the collector of the PNP will be very close to the supply voltage. And perhaps this could be used to power my alarm siren. That's connected to ground. So if I can get this latch into the on position for about 60 seconds, I can sound the siren and let everybody know that a burglar has entered my house. And if I can come up with some sort of a timing circuit that after 60 seconds will put the latch in the off state, then I'm very close to having my burglar alarm circuit. Now recall that in the capacitor video, we analyzed an RC circuit. And we said that resistance times capacitance, RC, was equal to time. So we could use this RC circuit to generate a 60-second delay time. And so in the next video, we'll analyze how we can use this RC circuit to get the latch in the off state once it's turned on.